k minus n. If k is indeed greater than n, then I assume that every element is going to be taken from B, okay, and then I'm going to only take a small number of elements from A. So that's kind of the lowest position that I will need to look at. But this is also a heuristic. And then J low is the same thing. If I assume that every element is going to be taken from A, then I can start by setting a low position of into the B into B as k minus n. So these are the kind of if you think about it, these are the kind of window. The I low and I, and J low and then J are going to be form the two windows. Hopefully, something inside that window is going to give me the real I value and the real J value at the end. Okay. So I'm going to start these two windows somewhat wide, and as I do the search, I'm going to move the window if necessary, and also I'm going to shrink the window, so that at the end the window will be exactly 1, and that will give me the answer, right? So I just keep zooming into the right position, and then I keep the property that I plus j will be 1. So I keep moving the window until I lock into the I and j positions. Does that make sense? Okay. So I loop until I find the answer. So if I find the answer, I'm going to say I'm not active anymore. And I'm going to test if I is greater than 0 and j is less than n, and I minus 1 is greater than b j. Remember those two conditions that I'm going to need to satisfy in my final answer, right? So as long as I minus 1 is greater than j, then I'm going to move my my pointer of I and j. So remember, the condition is actually less than or equal to, right? In the end, I minus 1 should be less than or equal to bj. So if I have a condition, if I see for the current I and j value, I minus 1 is actually greater than bj, what does that mean? I is too high, right? I is being set too high. I needs to come down, okay? And so this, and also I has to be greater than 0. If I is equal to 0, that means that I'm not going to take anything from A, right? I is 0 and I is still too high. That means that nothing from A is going to be there, right? So, so these conditions tell me that I need to lower the window of I and perhaps raise the window for B, right? So that I can reduce I and increase J, right, to be able to lock into the right value. So I would create a delta to be the I minus I low plus 1. So this is the current window size for A, right? The current window size for A. So I already know that I need to adjust it down, right? As I adjust down, I also shrink the window, right? So that I can both go close to that value and also narrow down the window so that I can begin to lock in, right? So that means that I'm going to take I low is going to become J low is going to become J, and then J is going to become J plus delta. Why? Because B is not big enough, right? When I lower I need to raise J. So I'm moving the window. I'm moving the window higher by delta. Okay, by delta. And the delta has already been divided by 2 here. So the new window size is smaller, right? It's smaller than the previous window. And I will be moved down, right? So I becomes I minus delta. Does that make sense? Okay. So so basically, I low is still going to remain the same, and J is going to be, I low is going to be the same, but I is going to be tuned down, moved down by delta, and then J is going to be moved up, right? And the window size is going to be reduced. So both window size will be now half of the window size as before, right? Okay. If J is greater than 0 and J minus 1 is greater than or equal to AI, that means that the J value is too high. Okay. Now you need to adjust the value so that the J will come down and I will go up, right? So the way we do this is I low becomes I, so the window will become, the window will be shifted up by replacing the original low value with the I value, and then the window will be, I will be increased by delta, so that I will go up, and then the J value will come down, so J will be reduced, but J low will remain the same. So this essentially just, whether you adjust I low and J low depends on whether the value is too big or too small. And then you move one up, you move one down, and you shrink the window. Okay. So that is the definition of a double binary search. Because you're doing binary search on two lists simultaneously. And these two lists are bound by that property I plus J needs to be K. Right? So that determines how you do each of these. And until neither this nor that is true, right? So if it becomes that AI minus 1 is less than or greater than B, but less than or equal to B, and then Bj minus 1 is less than AI, then you come down to here, right? When you come down to here, that means that you already found the element, okay? And that you said then it is inactive. That means that the while loop will exit, and then you will do the return of that I value. So that's where you found the value, okay? So this is the part that I did not talk about when you raise your hand, okay?
That's okay.
Make sense?
Yes.
Okay, very good. So, yeah.
What is the complexity of this? Max of...
It's a log n. It's a log n. It's actually truly log n.
Okay.
And so that's why it can be still dangerous, because if you have, let's say, millions of elements, the first thread and versus the last thread, there could be still like 20 times more work.
Yes.
Right, easily 20 times more work. When you take log a million, it's 20 times more. Okay. So, where is it? Okay. Okay. So, if you understand we're actually almost there for this lecture. I'm a little bit happier with this explanation than the one I had in the video. So hopefully I'm a little wiser than 2 years ago. Okay, I was looking at myself 2 years ago. I said, "You idiot! You could explain that way, right?" So, but if you're interested, go back and watch the video how I explained it 2 years ago, and then it's actually interesting. You may think that the guy 2 years ago was better, so if that's the case, come and tell me and make me feel better. Okay. So all the threads will divide up the output list into into the kind of the k current and the k next, right? The section. So you find that section, and then the output range of a thread from the C k current to k next, and then each thread calls the co-rank function to get I current and j current and I next, j next. Basically, the ij values for the previous thread and the ij value for your own thread, so that you can find the A and B little section, right? You can actually use that to partition that little section for yourself. So the kernel now looks like this. The kernel becomes extremely simple. Okay? So when you come in, every thread will use the linearized thread index, right? This is the linearized thread index. And then you will you will just divide up the C into these sections, right? And then you will use the end of the previous position and end of your own position, right? And then so you will be the elements, the slots or the positions that you need to fill are between the K current and the K next. And then you call co-rank. You co-rank with the K current, right? Which means that is the end marker for the previous thread. So you use the K for the previous thread, and you have A, M, B, N, and that gives you the beginning pointers, right? The beginning pointers of your own A and your own B sections, right? And then you call the co-rank again to get the K, using the K next, the end of your position, and then you A and B again. That gives you the ending markers, right, of your A and B. So then you use the beginning point marker and ending marker, and then you have the you calculate. You can calculate when you get the I, you can calculate your J by subtracting K, right, from your from the I. And then you use the K to subtract, and then you get a J. And then you can just take your little section of A and the little section of B and do a merge. Okay, just do a sequential merge, right? You do the sequential merge, and then you get, you do the sequential merge. So this is the sequential merge function, and then you write into that little section of your C, and that's it. So this is actually quite balanced, because all the threads are going to be only filling the same number of positions. So the total number of A and B elements that they need to visit in a sequential algorithm will be balanced across all the threads, right? But these two may not, right? So that's why the n-ary search is very important. Okay. Any questions? Yes.
Are we calculating every I and J twice?
Are we
calculating I and J twice using this kernel?
Are we causing any I and J?
Are we calculating I and J twice for each thread?
Because
he's asking if you
Calculating. Oh yes, yeah, absolutely. Yeah, so you're absolutely right. So because you're calculating for the previous thread, right? The previous thread is also calculating this value as its second value, right? So everything is calculated twice. So you already automatically did twice the amount of work.
Right. So can we use shared memory to?
Yes. So that points to the tiled algorithm. So that's exactly what we're going to start next time. Love it. So you guys are absolutely thinking. Okay. So we're going to have the tiled algorithm, and we're going to be using shared memory, and they're also potentially saving for this. Absolutely. Okay. So on Thursday. Okay. Good.